Okay, let's look at how rates are quoted, and given some sort of change in dollars, how do we communicate how much we earned? Or given some sort of rate, how do we calculate the change in dollars? So we want to talk about how rates are quoted and how we calculate rates of return. And we'll talk about this in two different contexts. The first is what happens within a year and what happens over multiple years. And we're just going to talk about standard conventions. And the idea is that if I start with $100 and I end up with 110, how do I communicate that to people? Well, if it happens in exactly a year, that's pretty easy. But if it happens in less than a year, or if it happens in more than a year, now the way these things are communicated changes. And so what we need to talk about are essentially three different measures. We need to talk about the annual percentage rate, the effective annual rate, and the annual percentage yield. And these two are synonyms. So the annual percentage rate is defined as the periodic rate times the number of periods, and we'll use a little m. And so if you're quoted a 6% APR on a mortgage, it's not 6% a year, it's really 0.5% every single month. And 1% per month is a 12% APR monthly rate. And this would be how a credit card would be quoted, for example. So if they tell you it's an 18% credit card, they don't mean 18% per year, they mean 1.5% every month. So 2% per quarter is going to be 8% APR quarterly, and 2.5% every 6 months is 5%. They will always quote the rate as the APR, as the annual rate. This is by rule, this is by custom, this is by law. So they will never, ever say it's a 1% per month credit card. They will always say it is a 12% APR monthly credit card. And bonds will never ever be quoted at 2.5% every 6 months. They will always be quoted as 5% APR semi-annual. And stocks, they will never tell you the dividend rate as 2% per quarter. They will always quote the dividend rate as 8% APR quarterly. So these are always quoted this way. So the next question is, if I have something that is quoted as a periodic rate times the number of periods, what is the equivalent annual rate? How much would I be indifferent between earning once versus some periodic return? And the difference, of course, is that the EAR is going to include the compounding and the APR will not. So we need to convert. So how much will I have at the end of the year if the amount I earned is 5% APR semi-annual? And I read this and I say, oh, okay, this means I get 2.5%, and then I get 2.5% on the principal and the interest I earned in the first 6 months, so there is compounding. So 5% APR means 2.5% every 6 months, so I'm going to earn half of 5%, I'm going to earn another half of 5%, I'm going to earn 1 plus 2.5% twice, and the amount that I actually earn is going to be 5.0625%. And what this means is if I start with $100 and I earn 5% APR semi-annual, I will have $105 and 6.25 cents. Or if I start with $100 and I earn 5.0625% once, I'll have the same amount. Next question, what is the quoted APR quarterly if we start with $100 and end with 110? Well, the annual return is 10%. That's pretty easy. This is the effective annual rate, but what quoted APR quarterly for periodicity M will give the same result? Now we have this equation. And so now I'm going to have my number of compounding periods is 4 because it's quarterly. And I'm going to plug this in, and I get 1 plus 0.1 to the fourth minus 1, and then again multiply this by 4, and this is going to give me 9.65% APR quarterly. So earning 9.65% APR quarterly, which is 2.41% every quarter, is equivalent with compounding to earning 10% annually. And we'll just go to a quick spreadsheet to look at some numbers. So I want to look at one thing on the whiteboard before we go to the spreadsheet. I want to look at the EAR equation, and that's going to equal 1 plus the APR divided by M to the M power minus 1. And what I want to think about is what happens when m gets bigger. When m is 1, well, this is obviously just the APR. And when it's 2, I take half the APR, square it. When it's 4, I take a quarter of the APR and take it to the 4th power and so on. Well, what happens if m gets really, really, really big? In fact, what is the limit as m goes to infinity? What does this turn into? And we'll try something that's very sort of similar. The limit as m goes to infinity of 1 plus 1 over m to the m minus 1. And let's go to the spreadsheet and see what happens to this value as m gets really, really big. Okay, so we're back at a spreadsheet, and I'm going to type m, and now I'm going to type in 1 plus 1 divided by m, and we'll take that to the m power. Put a line under that, center that, and we're good to go. Okay, so when m equals 1, what does this equal? And we'll center that as well. This is going to equal 1 plus 1 divided by that value to that value, and I can see that this is going to equal 2, and I'll add a couple decimal places. And when I go to 2, that's going to equal 2.25, and when I go to 3, that's going to equal 2.3704, and I can see that as m gets larger and larger, I'm adding a smaller and smaller fraction. I'll make that a little bigger, but I'm taking it to an increasingly higher exponent value. And so let's see what happens as this continues to grow. And I'll just pull down here, and I can see that this is getting bigger and bigger and bigger. There's 9, and let's go all the way down, and I get to 2.68. And I can go up here and I can just say, well, what happens when this gets to 100? What happens when this gets to 1,000? What happens when this gets to 2,000? Looks like it's pretty much maxed out there. What happens when this gets to 3,000? Looks like I'm pretty maxed out. What happens when I get to 10,000? What about 100,000? Okay. And what I'm seeing is that this value, the limit, as m approaches infinity, as I increase the number of compounding periods, I approach, well, exp of 1, I approach the value e. And so, if I have continuously compounded return, if I have a rate that is compounded not monthly, not weekly, not daily, but is compounded continuously, and this is theoretical, it's not physically possible to do so, then the equation for that, the EAR is going to equal, for a continuously compounded rate, it's going to be the exponent of the APR minus 1. And so that's going to be the value. So for example, 5%, if it's continuously compounded, 5%, if it's going to be continuously compounded, 5%, that's going to equal EXP, open parenthesis, minus 1, and I'm going to have 5.1271%. And what that means is that the equivalent of earning 5% compounded some really, really large number of times, so let's just do it. So this is going to equal 1 plus that 0.05 divided by, and let's have this be 10,000 compounding periods brought to the 10,000th, and then subtract 1 is going to equal 5.1271%. So continuous compounding is something we'll talk about on this next tab. And so on this next tab, here I have my two equations, and I have a couple of tables. And I've entered 5% just as a base rate. And here's the idea, is that I have an annual compounding. A 5% APR quote is equivalent annual rate of 5%. But if I have a semi-annual compounding period, if it's compounded twice, then 5% EAR is actually equal to a quote of 4.9390. And again, all we're doing is we're changing the quote. We're not changing the amount of money I get. I still get $105 on 100. I still get an extra $5, but I quote instead of 5% annual 4.9390. And if I'm going to quote a quarterly rate, then that's the same as quoting 4.9089. Here's monthly, here's daily, and then again continuous. So I am indifferent between 5% or 4.8790. They are not effectively, they are the same. It's just a question of how I am quoting it. And over here, I'm keeping the same APR quote, but showing as the number of compounding periods increase, the effective annual rate gets larger and larger. So 5% 2 times is 5.0625. 5% 365 times is 5.1267. And again, I can either get 5.1267 or I can get 5% daily. I am indifferent between the two. And here's the effective annual rate with that equation.